We are ready to study a new force of nature, a fundamentally new force. The four forces of nature, we've looked at gravity, but this is something new. So, let's enter in. And when we search in our environment for this new force, I have my little search probe here. And I will, if you're taking my class, you'll have seen this demonstrated or will see it demonstrated. But for right now, I'll just describe it briefly. So when I come to this sphere, we notice that it deflects, and that's a little bit different. It's not a contact force because nothing is touching. Moreover, it's not a gravitational force that we're familiar with because gravity acts straight down. And if you look at the force acting on this, gravity indeed is trying to make it go straight down, but something seems to be pushing it in a different direction than the gravitational field at that location. So there it is, pointing in this direction. So what is that force? It's not a fictitious force because we're in an inertial frame, which is not the case, for instance, if we're on a merry-go-round. If you sit on a merry-go-round and put a ball in front of you and let go, you'll notice the ball accelerate away from you. Because of your belief in the law of inertia, you decide that there must be a net force acting on the ball to make it accelerate. But from a bird's eye view, if you've got the merry-go-round, you look from way up here, looking down, you'll notice that there really is no net force, but you rather are moving away. You are in a circle, so you have an accelerated frame of reference, which is the difference between, the distinction here, between an inertial frame and an accelerated frame. You being in circular motion in an accelerated reference frame, the law of inertia does not work. So we call centrifugal force a fictitious force. Namely, it's a force that we ascribe to the observation we make of the ball that's sitting on the merry-go-round accelerating away from us. It's not a real force. Okay, enough on that little sidetrack. It also depends on the position from the interacting object. So if we're closer or farther away, it's different quantities of force. Now, so we think about this, it's non-contact, and we think maybe it's from a force field kind of like gravity, even though we know it's not gravity. Now, as we experiment with this, as you get experience with this, or just accept the experiences of others, you will notice some of the characteristics, and that is that it can attract or it can repel. Now, gravity is just attractive, right? So this one can do both. So here's a repulsion, but in a different situation, we have an attraction, as you may have already seen. Now, the size of the force depends on the distance from the interacting object. So that can be observed by this angle. Larger angle, larger force, smaller angle, smaller force as we move away from the interacting object. And it can be undone. So there's different ways to undo it. You can ground it, which I'll describe more later. You can light a match, make some plasma, and undo the effect as well. Then the geometry of the bodies affects the size of the force. This is just a small detail that isn't all that important, but we'll usually deal with symmetrical objects like a sphere, where the size of the force that we're talking about kind of is the same no matter which direction you look at it. And so we're not going to worry about this little detail very much, about the different geometries. Let's forge ahead. Now, this force effect that we're discussing can be obtained in different ways. And I'll just mention again that this is much better served if I can demonstrate this to you, which I will again if you're taking the class. So, but I will just briefly describe what you would be seeing at least. So the first method to obtain this effect is just by friction. Namely, we take a balloon, we rub it with a piece of fur. And then we notice that the balloon has a funny effect on those surrounding objects. It's attracted to objects close by it, like your hand or face or whatever. You rub a rod with fur now, and you place it near the balloon. And before it was attracting, but you do this, you rub the rod with fur and put it near the balloon, and guess what happens? It repels the balloon. Kind of interesting. So, based on this, you might think that something is being transferred as a result of an external friction force. We put friction on the balloon and observe this attraction. We put friction on the rod, between the rod and the fur, and then there's a repulsion between the objects. Maybe something is transferring from friction. Have you ever scuffed your feet, your stocking feet in the winter on your carpet and then touch your cat on the nose? Well, you might get a nice wow from that. If you do it to your dog, you might just not care because they're a little more stable in their emotions, I might say. But in any case, you can get a spark, and that is similar phenomena. So that's method 1. Method 2, I'm going to call it conduction. So conduction or contact. If you bring a rod toward a sphere, first it attracts. So there's a little sphere hanging down. You bring the rubbed rod toward it, and that sphere moves toward the rod. And then, after the sphere moves toward the rod and clunks into it, touches it, it springs back, flies back, repels right after touching. So we have the hanging sphere. We bring the rod in close, and we notice the attraction. I wonder what's going on when contact is made. I just don't know. Then immediately following that, we notice that the sphere repels. It's very interesting. Maybe something is being transferred as a result of contact between the object, causing these effects. So we have friction. We just have simple contact. Notice nothing was rubbed here, but it just touched. So there's the first 2 methods of obtaining the effect. And now for one more. Okay, and now we come to method 3. And method 3 is called induction. And it's a little bit interesting, and you have to kind of see it probably to truly visualize it. But I'll give you the basic sequence and then show you in pictures here. So first we touch a conducting sphere, and that touching is called grounding. And the grounding has a special meaning. Observation number 2. You bring a rubbed rod. We saw it had effect before. You bring it near that sphere that you're holding onto. Then you remove your hand, immediately followed by the rod, before there can be any contact between the rod and the sphere. What happens then? Now you bring the rod back toward the sphere, and you notice an attraction. Now you might be thinking, well, we saw that before. Yes, but in this case, the attraction is much greater. It has a significant attraction of the ball toward the rod. Well, so we obtain this effect without ever touching the rod to the sphere. So it must be able to occur without something being directly transferred between the 2 objects since they never touched. All right. First of all, I know you're just sitting on the edge of your seat wondering what these somethings that I've been referring to are referring to. And what they are, if you have not yet figured it out, they're charges. And those charges have a particular nature. They're either a plus or minus. So here we have our sphere. And it's hanging there under the influence of gravity. And it's got positive and negative charges in this conducting sphere. Now the positive and negative charges are, in fact, electrons and protons ultimately. But we're going to think of, well, the electrons are free to move around. The protons are not. They're held in place in the atom. But we're going to think of the positive and negative charges as just that. And really, a functional way to think of them is negatives being electrons. And if you take an electron and move it off an atom to somewhere else, now you have a positive ion. In its wake, it left behind a positive ion. So there's a positive charge. So those positive ions are in a sense mobile from the standpoint that if an electron jumps away from it, not from the positive, but from an atom, and an electron leaves the atom, it leaves a positive charge there. And it can, wherever the atom leaves from, that's where the positive charge goes to. Now, there can have a chain reaction effect, so to speak. The electron can bounce along, and the positive wake, so to speak, bounces in the opposite direction. So just keep in mind that functionally we're allowing charges to be free to move, and positive and negative, doesn't matter really from whence they come, they are going to be free to move in a conductor. And most things are neutral. So we start with our conductor being neutral. And I just show that there is positive and negative charges waiting to be moved around here, but there's equal numbers of them. Overall, the atom is neutral. A very precisely placed hand. And the hand touching the neutral sphere is what we call ground. So we're grounding the sphere, which means we're placing it in contact with something that is going to neutralize this if it's not already neutral. That would be the hand. Ultimately, it's usually the planet Earth itself. More often than not, a hand is attached to a physical human body, which then is standing on the ground. So charges are able to come and go between the object and the Earth readily by grounding it. Grounding is also a safety measure. In electrical systems, like in your house, you have a wire. It's the grounding wire. And so if you're touching, if you've got a hold, if there's a short circuit somewhere, or the hot line of the 120 volts connected to the chassis of some appliance, instead of it, when you touch it, you may provide a path to ground, and that's really bad. That can do damage to you. But if it's grounded already to planet Earth through that wire, the dangerous electricity, the dangerous current flow will pass through that instead of your body. So it's a protection measure as well. All right. Now, here we have the rubbed rod, and we're going to bring it near. When we bring the rubbed rod near, since the charges are free to move around, they will, in fact, do that. And I'm putting a ground symbol here. This is your hand touching it. So the charges can come into this or go out of it. So it's a negatively charged rod that you're bringing close. And you probably know that likes repel, opposites attract. So that is, in fact, what's going to happen here. It's going to attract the positive, repel the negative, which is then pushed off into ground, leaving the sphere. So charges are pushed off the sphere and end up going into your hand. That's grounding it. And then finally, we have a charged sphere now. And we bring the negative rod close, and indeed it tracks it very strongly because we have these excess positive charges in there, and unlikes attract. No contact ever occurred between these objects. So that's how we charge by induction. And you'll notice the charged rod and the charged sphere are opposite signs. When you charge by induction, you get the effect is to charge the object with the opposite sign. That's about enough physics fun for right now. In the next video, we'll enter into a discussion of induced charge separation. You won't want to miss it.